first algorithm we're going to talk about is called the nearest neighbor algorithm. And here's how it goes. First, we're going to start from our home city. Then, visit the nearest city to the home city. And the nearest one is based on whichever one has the lowest weight. In this case, number of miles, but I mean, it could be like a cost, like a dollar cost in traveling from city to city. But this algorithm says start at your home city and then visit the next closest city. Then, do that again. Visit the next nearest city that you haven't already visited. And finally, you're going to keep doing that until you have to return home when no other choice is available. So let's apply this nearest neighbor algorithm to the first example, and then let's do another example with 5 vertices. Because in this one, we were pretty easily able to find the actual minimum cost. But with 5 vertices, we would have, 12 to list, and that's a lot to check. And on your worksheet, you're going to have one with 6 vertices, and I doubt you'd want to list out 60 Hamiltonian circuits. I mean, you might as well travel a few extra miles. But what does the nearest neighbor algorithm give? And how am I going to do this? I'm going to use a different color marker. So the nearest neighbor algorithm, we're starting at Chicago, remember? So we're starting here. And we're going to go to the nearest city. So what choices do we have from Chicago? 425, 300, 349. Well, the smallest one there, 300. So that's where we're going first. St. Louis. And then what? What are our choices here? Well, we have 541 and 562. We can't go back to Chicago yet because we have to visit Detroit and Minneapolis first. So here's St. Louis, 541, 562. 541 is smaller. So that's the one we choose. Now, from Detroit, we have only one choice. We have only to go to Minneapolis and then back to Chicago. So this algorithm gave us that circuit. And what is, C to S to D to M to C. And what was the cost of this one? I don't know, what is it, 12, 17? I don't know, I must have this written down somewhere. 2,040 miles? Oh, 12, not 17, 12, 19. Okay, that's why I was getting. I was thinking 1,200 plus 700 was 17. Gives this, which has 2,040 miles. So this algorithm on this example did not give the optimal solution. Let's look at another graph. Let's look at this graph, and I'll throw some numbers on it. So this graph here has 5 vertices. Let's do one, or 4 vertices. Let's do one with 5 vertices. That graph on 4 vertices there, in that graph we've had an edge connecting each vertex to each other vertex. When that happens, the graph is called a complete graph. When there's an edge connecting, exactly one edge connecting each vertex to each other vertex, it's a complete graph. And what we're doing here is we're actually, there's always going to be a distance between cities. So all of these graphs are going to be complete graphs. And one way you can check whether a graph is complete, in that previous one we had 4 vertices. Each edge, or each vertex had 3 edges coming out of it. Here we have a complete graph on 5 vertices, and each vertex has 4 edges coming out of it. And let's put weights on these. So we have 600 up here, 700 here, 500 here, 800 here, 400 here. This one will be 950. This one in the middle will be 750. This diagonal thing here is 650. This one here is 550. This one down here is 850. Is that all? 1, 2, 3, 4, 5, so yeah, 10 things, so that's all of them. So what we're going to do here is apply, we're going to do a couple different ones. So let's apply, in this example, apply nearest neighbor algorithm starting at, let's do 3 of them. Let's start at A, let's start at B, and let's start at C. Apply the nearest neighbor algorithm starting at vertex A, then vertex B, then vertex C. And in the first example, I shaded in the graph. In these, I'm going to do it slightly differently. I'm just going to draw these nodes and fill in the edges as the algorithm tells us. So first we'll do start at A. So here's A, B, C, D. So start at A. Well, what are our choices from A? That's a D. What are our choices from A? 700, 550, 650, 600. Which one's smallest? 550. And this way that I'm doing this example here is actually also useful because it makes it very, very obvious which nodes we haven't visited. If I'm shading things in, I mean, there are colors all over. It might not be immediately obvious, but right here we see we haven't hit B, C, or E yet. So we went from A to D. Now from D, what are our choices? 400, 850, 800. Now, notice I didn't say 550 because we already visited A. So we have 400, 850, 800. So let's choose 400. Well, the algorithm says choose 400. Okay, now what? Well, if you look at that, all we can do is go to B or C. So B and C, we have from E 950, we have 750. 750 is smaller. So we have the 750. And from C, we have only one choice now. Up to B and back to A. Because we can't visit E, A, or D again without visiting B. And then we go back to A. So visit B is cost of 500. Visit A is cost of 600. So we have this circuit. And what's the cost? Well, maybe I'll say, I should say what the circuit is. Circuit is, what was it? A, D, E, C, B, A. And what's the cost? Well, add these numbers together. Now, these you don't need a calculator for. These are, I mean, they're hundreds and fifties. You don't need a calculator for that. 1,100 plus another 1,300 makes 2,400, and 400 makes it 2,800. And it probably would have been easier if I did 400, 500, 600 makes 1,500. 15 plus 13, 28. But here, starting at A, we got that circuit. What if we start at B? Start at B. Well, again, I'm going to draw out the edges. Not the edges, the vertices. Start at B. Well, what's the cheapest one from B? 600, 950, 850, 500. Sounds like 500. And then we're at C. Now from C, what's cheapest coming out of C that isn't the one to B? 650, 750, 800. So the smallest is 650, and that brings us up to A. Now from A, what do we have? We have, well, we can't go back to B or C. We need to go to E or D first. 700, 550. So we'll choose the 550. And then from D, we can only go back to E, which is 400. And then back to B, which is 950. So here the circuit is, what was it? It was B, C, A, D, E, back to B. And what's the cost here? This one's more annoying with all these 50s. So what is it? It's 1,200, 1,700, 2,100, 30, 50. So the cost is 3,050, whatever units we have here. And next it tells us to do it starting at C. Starting at C. Well, again, I'm going to draw out the vertices. Draw out the vertices. This way, where I draw out the vertices, is actually going to be a much better way to do the next algorithm than filling this graph in, because it'll make the places where the algorithm can go wrong much more clear. In this one, it's not too bad filling in the original graph with shaded in lines, but in the next one, I definitely think it's much harder to fill in the graph. But we're doing what? Starting at C. So what are our choices? C, 500, 650, 750, 800. So the cheapest one there, 500. From B, the cheapest one, we have 600, 950, and 850. Cheapest one is 600. Over to A. Now from A, what do we have? We have 700 and 550. So 550 is cheaper. And then from D, we can only go back to E at a cost of 400, and then back to B, a cost of 950. So the circuit is, what did we, oh wait, what am I doing back to B? That's the type of mistake if I made in lecture. Half the class would be yelling things out at me, which is okay. That's what you should do when that happens. Back to C. Well, it's what you should do in my class when that happens. I won't speak for other classes. But this was starting and ending at C, so we went back to C. And going back to B didn't even make a circuit. Well, it made a circuit, not the one we wanted. So the circuit is what? C, B, A, D, E, C. And the cost is what? 1,100 plus 1,300 is 24, and 4 makes 28. And cost is 2,800. Notice, starting at A and starting at C, we got the same exact cycle. That is possible with this algorithm. I don't know what happens if you start at D or E. Looks like you should see what happens when you start at D or E as an exercise. When you start at D, what do you get? You get D, E, A, B. What do you go? You go all the way around. So D, E, A, B, C, and back to D. So when you start at D, you should verify this. You get D, E, A, B, C, D. When you start at E, what do you get? You get E, D, A, B, C, D, which is also distinct. So this algorithm doesn't necessarily give the minimum cost, but it does give a circuit. It does give some restriction on the cost of the circuit, and that's especially useful if we have, if you have like 300 vertices on this. It would be useful to get some restriction on visiting each node. But let's look at another algorithm.